What gives the symbols we use in mathematical notation their meaning? My name is Theresa Wege. I'm a doctoral student at Loughborough University, and I want to explore this question with you today. We'll look back in time and combine approaches from philosophy, cognitive science, to explore iconicity in mathematical notation. Let's start off with looking at mathematical notation. What we see here are basically just differently shaped and sized scribbles. Imagine showing this page to a person who lived 10,000 years ago or to a small child. It would mean nothing to them. However, for us, mathematical notation conveys meaning. Humans created mathematics, and as we went along, we made up and developed ways to write down these ideas. A certain scribble conveys the idea of three, and a simple line conveys the complex mathematical idea of subtraction. The fundamental topic of my talk today is to ask whether notation is arbitrary or whether some scribbles are better at conveying certain mathematical ideas than others. We can think of the scribbles used in notation as either symbols or icons. This terminology and distinction was introduced by Charles Peirce. A symbol gains all its meaning from our shared knowledge. The scribble of the number 3 looks nothing like the concept of threeness. But we all share the knowledge of what is conveyed with this notation. Icons, on the other hand, do have visual properties that tie them to their meaning. Iconic notation does not consist of completely arbitrary scribbles that only gain meaning through what we use them for, but some meaning is already conveyed in how the notation looks like. In our research, we want to explore this iconicity and its role in mathematical notation. One of the first researchers to think about iconicity was Christine Ladd. She was the first woman to fulfill the requirements of a PhD in mathematics and logic at Howard University, but she was denied her degree until a few years before her death in 1930. During her time, the field of formal mathematical logic flourished, and there were ongoing discussions about how to develop a notation for logic. Here you can see a few different notations that can be used to express the logical implication A implies B. Ladd made substantial contributions to the field of logic, but for us most remarkably, she weighed in on the discussion around notation by suggesting that unsymmetrical symbols should be used for unsymmetrical relationships. If we unpack the statement a little further, we find that her main idea was that notation is symmetrical along a vertical axis somehow better conveys the mathematical concept of commutativity. In other words, a symbol that can be mirrored from left to right without changing is iconic of the idea that we can mirror an equation from left to right without changing the meaning of it. We were fascinated by this idea and aimed to test Ladd's hypothesis empirically. There are two parts to testing Ladd's hypothesis. First, are symmetric symbols really intuitively associated with the mathematical concept of commutativity? And are they hence iconic? And second, is this kind of iconic notation really advantageous for engaging with mathematics? Here's how we tested the first question. We designed an experiment that asked 30 students to evaluate whether a statement about commutativity was true or false. Here's an example with addition. We know that the statement here is true. Changing the symbol to the minus sign, and we know that the statement is false. This operation is not commutative. Now in our experiment, we didn't use any symbols that already have mathematical meaning, but we showed our participants some unknown non-mathematical symbols and asked them to simply guess whether they think the statement is true or false. Here you see the symbol presented being symmetrical along a vertical axis. If this symmetry is really iconic of the mathematical idea of commutativity, our participants should more often think that this statement is true compared to this statement where the symbol was flipped by 90 degrees and is not symmetrical along the vertical axis anymore. And indeed, this is exactly what we found. Without knowing anything else about these symbols, just the fact that they were symmetrical along the vertical axis meant that people intuitively associated these statements with commutativity. We found iconicity in mathematical notation. So now that we know what kind of notation is iconic of commutativity, we can take a look at whether that is at all relevant and maybe even advantageous for actually doing maths. To look at this question, we designed another experiment. This time we looked at how quickly students could solve arithmetic problems when the usual notation of plus, minus, times, and divide was replaced with symmetrical or non-symmetrical iconic notation that they had to learn. For some students, the new notation lined up with the commutativity of the operations they had to solve. So they learned vertically symmetrical symbols for the commutative operations, addition and multiplication, and learned asymmetrical notation for the non-commutative operations of subtraction and division. The other half of our students learned the symbols the other way around, now having symmetric symbols convey non-commutative operations. We looked at how many questions students in both groups could solve in a given time. The idea here is that if iconic notation indeed helped students to remember what mathematical concept is conveyed, then the students should have an easier time solving the problems and solve more problems overall than students who were using non-iconic notation. Again, this is exactly what we found. Iconic notation was advantageous for our students, and they solved more problems than the students who were given the opposite notation. So let's summarize. In two experiments, we could show that symmetry in notation is indeed iconic, and just looking at a symmetrical symbol conveys some association with the mathematical concept of commutativity. And further, that using this kind of iconic notation was advantageous for students engaging with mathematical problems. So coming back to Christine Ladd and her proposal from 140 years ago, using our assessment of her philosophy and her original proposal, and then employing empirical methods from cognitive science, we investigated her general idea that notation could be iconic of the mathematical concept that it conveys, particularly in the case of symmetry and commutativity. From our findings, we conclude that there seems to be no obvious downside and a plausible upside to following Ladd's principle when choosing which symbols to use when teaching mathematics. Now, of course, we don't mean that all mathematical notation should be changed. Rather than whenever there is a choice of notation, we would recommend to think, which one would Christine Ladd prefer? For example, teaching division using the dash rather than the colon could benefit from the fact that a non-commutative operation is now conveyed by a symbol that is non-symmetrical and represents the concept in an iconic rather than just a symbolic way. Another case where we could ask what notation would Christine Ladd prefer is when introducing group theory in undergraduate mathematics. There might be benefits to using symmetrical notation only for commutative groups. If you're interested in our deeper assessment of the topic of iconicity in mathematical notation, I'm happy to tell you that our manuscript has been published in the Journal of Numerical Cognition. You can find a link in the description. I want to thank my co-authors, Sophie Batchelor, Matthew Engels, Manali Mistry, and Dirk Schlimm for working with me on this project. And thank you for joining me for this presentation today.